you, Mr. Sinha, for instilling a positive momentum and highlighting India's potential on becoming a global powerhouse in EV manufacturing and technology. Next up, it's my pleasure to invite Mr. Ashim Sharma, Senior Partner and Group Head of Business Performance Improvement Consulting at Nomura Research Institute, NRI. He'll present and share his thoughts on the topic pivoting for the next wave of the EV revolution.
The topic of my presentation today is going to be pivoting for the next wave of the EV revolution on this momentous occasion of the World Environment Day. So I think there are 6 areas that we need to focus on when we talk about pivoting for the next wave of the EV revolution. One is securing the anticipated battery demands, then exploring non-rare earth materials for EV motors, development of EV-specific platforms, enabling ultra-fast charging of EVs, promoting circularity through reuse and recycling, and finally, and very importantly, also upskilling workforce with developing technologies. Moving on to the first one, which is securing the anticipated battery demand. Well, it's clearly seen that the demand for EVs in India is expected to grow manyfold as we move from 2022 to 2030. And also at the same time, the global LIV demand is also expected to increase to about 3 terawatt hour by the year 2030. But when we look at the current state of the battery raw material value chain in India, we see that as far as raw material reserves, raw material mining, and raw material processing, as well as electrode materials is concerned, we haven't been able to make much progress. One of the factors that are causing this is there is no significant availability or access to key raw materials like lithium or cobalt, and very limited capacity to process the raw materials in case we get them in unprocessed forms. Very few companies, mainly startups, have started developing active electrode materials and electrolytes for the batteries. So even in that, to that extent, we are still nascent. As far as cell manufacturing is concerned, some plants are coming up primarily on the back of the ACC PLI scheme of the government. But as far as complete pack assembly is concerned, many domestic and international companies are present in India, and a high level of localization has been achieved therein. Now, looking at some of these things slightly more deeply, when we look at reserves, well, we understand that most of these are in countries outside of India. We have about 5.9 million metric ton discovered reserves, but still not proven. If you look at the other elements, that is cobalt, nickel, magnesium, and graphite, again, for all of those, we are dependent on countries outside of India and not much of reserves that are present over here. Therefore, since we lack sufficient reserves of these key materials like lithium, nickel, cobalt, we are dependent on imports. Hence, there is a need to explore alternate ways of securing these raw materials so that our supply chains remain resilient. When it comes to mining, again, due to lack of reserves, mining activities for key materials are non-existent as of now. We have a JV by a company by the name of Kabil, which has share of the National Aluminium Company, Hindustan Copper, and the Exploration Corporation. They have signed a preliminary agreement with Australia's Critical Minerals Facilitation Office for 2 lithium, 3 cobalt mining projects in Australia. That is where it is right now. In terms of refining and processing, again, limited capabilities exist. For lithium, there is only one company in India, Manikaran Lithium, which is setting up a proposed lithium refinery in Gujarat. In cobalt, again, refining capacity is estimated at about 2,000 tons per year, with Nicomet Industries and Kunkolim Goa and Rubamin Vadodara being the leading producers. In case of nickel, of course, there's Hindustan Copper, which has inaugurated its first nickel production plant in 2016 with about 50 tons per annum capacity. So again, then we see due to lack of reserves, limited raw material mining and processing capabilities exist. We would probably need to acquire or develop these capabilities also so as to be able to process battery grade materials from raw materials once they become available. When we look at the current control over the production capacity of battery grade materials and cells going up to the year 2030, we see that China is amongst the top 5, and in fact, the leading country having control of the production capacity, whether it is in cobalt, where they control about 51%, lithium about 34%, nickel about 59%, and manganese about 56%. And therefore, there will be a need for us to develop some of these sources, or also acquire through some partnerships, etc., because we need to rely on imports. And for whatever reserves we have spotted, which are yet to be proven, again, amongst the different extraction technologies, which is brine extraction, spodumene mining, as well as direct lithium extraction, DLE or direct lithium extraction may turn out to be the most viable, because it has minimal damage to the ecology of the region as well. So that is another capability area that India will have to develop, while at the same time also exploring partnerships with countries such as Australia and Canada to also de-risk the supply of some of these materials to us. Next, we come to electrode materials. Again, there is a dire need here to develop active electrode materials for cell manufacturing. It takes a lot of R&D effort and is patent protected, with most companies having established this technology in China. There is a need for us to replicate some of this in India, so as to ensure that we have the recipe maker or the chemist in-house who can tweak some of these chemistries in the face of geopolitical reasons, such as shortages of certain materials, or prices of certain materials rising dramatically, or also to develop battery chemistries from non-rare earth materials, wherein things like sodium ion, etc., are talked about. So therefore, this will be very essential also to develop within the country as a competence. Moving on to the next topic, which is exploring non-rare earth materials for EV motors. Here again, if we look at the spectrum of EV motors, there are AC motors, where alternating current is used to power the motor, or DC motors, where direct current is used. Again, the AC motors can be divided into permanent magnet synchronous motors, or PMSM as they are called, the three-phase induction motors, reluctance motors, or in the DC motors, there is the BLDC, or the brushless DC motor. We see that there is a lot of application of the PMSM in PV, LCV, MNHCV buses greater than 9 meters, and use of rare earth materials here is high. Of course, the three-phase induction motor, which is also used in some PVs and LCVs, does not use rare earths, and same is the case with the reluctance motors also. But when it comes to rare earth materials in motors, and a lot of vehicles still use these, we see that neodymium, which is mostly used and is a powerful magnet for speakers, hard drives, electric motors, which is mixed with certain additives, is the most widely used rare earth combination. And we know that for every ton of rare earth that is mined, up to 1 ton of radioactive waste and 200 cubic meter of acid containing sewage water, as well as about 27 to 28 tons of CO2 is produced. And again, rare earths are at the top of most nations' list of critical materials, and they're financially unsustainable as well as environmentally problematic based on the emission levels that I just spoke about. Also, India just has 6% of the world's rare earth reserves and produces only 1% of the global output. Here again, we are dependent on other countries such as China, and therefore there is a need to innovate and develop substitutes for rare earths, which is also known as lab magnets, etc., so as to be able to move away from rare earths, both from geopolitical as well as environmental reasons. These are some of the alternatives to rare earths that we are seeing, for which research is underway. One of the alternatives to neodymium iron boride as a permanent magnet is simple ferrite. Other permanent magnet materials of the market include aluminium, nickel, cobalt alloys, which form well at high temperatures, but could easily lose their magnetization as well. Then there is samarium cobalt, which is another rare earth magnet similar to the neodymium iron boride, but handles high temperatures even better. The cobalt-based alloy steel used in motors for EVs, with some variations from mainstream designs, provides the highest magnetic performance and strength along with the lowest weight. So these are some substitutes that are being talked about as far far as rare earths are concerned. At the same time, we are also seeing magnet-free technology in motors like the switch reluctance motor coming in. While previously, the switch reluctance motors had more of the torque ripple and would not operate as quietly, but now we are seeing algorithms and electronics being overlaid over these, trying to make their performance come as close as the permanent magnet motors. Additionally, we also see synchronous reluctance technologies, which combine the performance of permanent magnet motors with simplicity and service friendliness of induction motors. This is again a technology which will reduce also the environmental impact by using less electricity and reducing CO2 emissions. So that's the other paradigm that's being talked about, which is the magnet-free technology. Many companies, whether it's Tesla, ABB, or even the homegrown company called Chara Technologies, is working and developing these technologies so as to move us away from rare earth materials and motors. Coming to the next one, which is development of EV-specific platform. Here again, we see there are traditional platforms which are more suited for ICE engines, and therefore also companies such as Volkswagen develop the MQB platform, ensuring flexibility with multiple drivetrain options. But now we see there is a complete movement towards the EV platforms, which are dedicated EV platforms. They, of course, need a lot of R&D spending in terms of time and money, but various OEMs are adopting them because they are tailored to the vehicle performance needs of EVs. They have weight only at the right places, which the battery and the EV powertrain need, wherever they need those reinforcements. They are flat beds, so there is a flat bed assembly, so it decreases the interior space. Also, they can support a wide variety of body designs. Of course, they are modular and flexible as well. And there are multifold opportunities for lightweighting in them as well. So what we call born electric bespoke EV platforms is the way to go forward. And as we can see on the chart, many companies, very leading companies globally, as well as Indian companies, are talking about releasing car models on these dedicated EV platforms. And this is not just limited to cars. TVS Motors has also recently talked about releasing a two-wheeler on a born electric platform under the name TVS X. Next topic, and very important one, is enabling ultra-fast charging. We see that in order to bring parity with ICE vehicles, a lot of efforts are being made to develop ultra-fast charging for the electric vehicles. And here we see that there are a lot of trends that are shaping this, some of which are already market ready. For example, battery innovations being done for faster charging at lower costs, open charge protocol, which is OCPP 2.0.1, smart energy management and charging algorithms, seamless payment options, and also, of course, the architecture moving towards 400 volts or 170 kilowatt hour charging, and ultimately then moving towards 800 volt or 350 kilowatt hour charging, which also, is able to minimize losses and enable ultra fast charging. We see a lot of recent developments have happened in this case, or launches are expected to happen in the near future, whether it's the Blade battery by BYD, which is expected to include a 800 volt structure and charge 90 miles of range only in 5 minutes. The new Audi e-tron, the Porsche Taycan, released in 2019, already has an 800 volt internal architecture. The Kia EV6, based on the eGMP platform, includes 800 volt charging speeds and charges 10 to 80% in just mere 18 minutes. Of course, there are challenges with ultra-fast charging, risk of overvoltage, overcurrent, risk to personnel involved in installation, maintenance, and improper handling can reach to larger shocks. Of course, the electronics need to be upgraded to handle such high voltages. Also, there is a need to ensure the durability and reliability of the components under these high-stress conditions. And of course, compatibility and interoperability of the entire charging network will also have to be done. In fact, an upgrade of the charging networks would also need to be done. Also, manufacturing such charging equipment can be more expensive due to the need for specialized components and materials, and also maybe some global standards may need to be established. So there is a need to develop competencies in this area as well. Also, we see that, with the rising number of EVs coupled with fast charging capabilities, they will also pose challenges for the electricity grid, as you can see in this chart. So, the upper range in 2030 in terms of the terawatt hour requirement is going to be huge across different segments. And, the total electricity demand could vary between 37 and 97 terawatt hour, under 33% and 100% EV penetration in 2030. And therefore, there would be a need for managing the voltage instability and phase unbalance, because the EVs consume a large amount of power in a short time. So single-phase EV chargers increase the phase unbalance at the distribution network, and therefore there would be a need to upgrade some of this infrastructure. Also, overloading of the distribution network components could happen as the EV energy demand requires a large amount of electric energy to be transmitted from the generation stations to the distribution networks. Therefore, the network equipment such as transformers, cables may get overloaded due to the new EV loads. Then also there could be harmonics distortion happening, generation of frequency other than 50 hertz of the fundamental frequency, which could cause power loss. So the transformer and the cables could get heated, and this could lead to a decrease in the component's life. So the entire grid infrastructure would also need to be upgraded in order to manage some of these things. Certain interventions already being talked about, which is like the optimal charging algorithms, which is like smart charging. It flattens the load curve, increases the the life of the power distribution components like transformers and cables. Concepts like vehicle to grid also helping reduce this. Also, delayed charging, which controls the charging time and charges EVs only during off-peak hours. This reduces the cost and helps the grid operate smoothly. So that is one solution. Then the use of energy storage systems, the BESS systems, which can reduce the EV charging costs, reduce the, improve the reliability and resilience of the charging network, also increase the EV charging capacity and enhance grid stability. And finally, and very importantly, also integrating renewable energy in the grid, like solar or wind, which can be locally integrated into the charging station in the form of what is called a microgrid. PV ESS coupled plant can also support charging during non-peak generating hours, and the users can take the advantage of net metering, where they earn credits by transferring the surplus energy to the grid from these microgrids. The next topic is promoting circularity through reuse and recycling. We understand that India can implement crucial policies and regulations to prioritize the recycling of batteries. A lot of those regulations have also been talked about, as you can see in the blue box on this chart, whether it's the e-waste rules 2011, 2016, 2018, which provide an initial framework for effective e-waste management, material recovery, and reducing hazardous disposal. Then there are the battery waste management rules, which were introduced in 2022. Also, the policy sets an ambitious recovery target, 90% of the batteries placed in the market by 23-24. So the batteries that will be placed by 23-24 by 2027 for the EV batteries, and for the other batteries by 23-24. Also mandates a use of 5% recycled material in new batteries manufactured from 2027, and to be ramped up to about 20% of the reuse of recycled material by 2030. Of course, there are some challenges as far as recycling is concerned. First and foremost is securing sustainable supply of feedstock for materials like lithium, cobalt, and nickel, given that the existing park is small. Also, the chemistry of batteries is evolving and driven by enhancements in performance, cost reductions, which complicates recycling by necessitating adaptable processes that can adapt to these changes in battery chemistries, and also keeping up with technological advancements like changes in battery designs, and ensuring that they are more conducive to disassembly, etc. We are seeing that battery recycling supply chain is reshaping, with cell makers and battery integrators becoming increasingly involved in this battery recycling business. As you can see here, we see cell makers going all the way to becoming recyclers, as well as auto OEMs backward integrating as well, along with recyclers. So what we have is basically three types of players: vertically integrated recyclers, cross-value chain players, which provide an end-to-end recycling solution, and in-house OEM recyclers. And we see many examples of OEMs doing this, whether it's the Volkswagen Group's pilot plant for battery recycling, which has been set up with the goal of recapturing about 95% of the materials in the EV battery pack. Umicore and Audi are exploring strategic research cooperation for closed-loop recycling and recovering 90% of the cobalt and nickel from lithium modules. Then we are seeing BMW, Northvolt, and Umicore. Also, Hyundai Motor Group is participating in certain partnerships of that sort. Closer home in India, MG Motor India and Etero have forged a partnership for reusing and recycling end-of-life EV lithium-ion batteries. And similarly, Renault and GM are also looking at, are also taking steps in this direction. Finally, coming to the upcycling workforce and developing the technologies, we understand that the push towards electrification will require significant skill upgradation in specific disciplines, in areas like battery chemistry, electric drivetrains, autonomous features, and also to drive innovation and create competitive advantage by developing the cutting-edge EV technologies. Therefore, whether it's electrical technologies, sensing, actuation, AI, ML, composite materials, also more and more knowledge and skills around computer and data science, whether it's the things that are going into power electronics, electric motors and drives, signal image processing. Also in terms of manufacturing, more and more things around working with advanced materials that would be coming in. Also manufacturing in terms of developing different cell chemistries and developing cells with those different kinds of chemistries, control systems, thermal management, as well as in the after sales and service to be able to service the electric motors and drives, to be able to diagnose, repair, and maintain electric vehicles, as well as in battery management systems, whether it's in the form of over-the-air updates, etc. A significant amount of reskilling of the workforce will be needed across the value chain, and that is another area that must be focused on. So these are broadly the 6 areas that we need to focus on in order to be able to pivot ourselves to develop sufficient competitive advantage in the country for the next wave of EV technologies. Thank you very much for a patient hearing.